Hello, and today's topic is about the synchronized connections. The synchronized connection classes include vector hash table and the synchronized wrapper classes created by the collection's synchronized factoring methods. These classes achieve thread safety by encapsulation their state and synchronizing every public method so that only one thread at a time can access the collection state. The synchronized collections are thread safe, but you may sometimes need to use additional client-side logging to guard compound actions. Here is an example. In the following example, although vector is thread safe, the get lost and delete lost didn't use client-side logging to guard compound actions. As a result, get lost sometimes can throw index out of bound exception. Let's copy the code to Eclipse and show you how the exception is thrown. Let's go back to the Java view. Open Java view. Okay. Delete this. We have this class. So one scenario is thread A, after executing this line, thread B just executed this line, and the list have one element less, but thread A didn't see the change. It's trying to get the lost element, and at that point, an index out of bound exception will throw. So let's run the program. First, you see that there's two threads. The main thread created the list, and then it's trying to get the lost element. At the meantime, another thread is trying to delete lost, depending on which one wins. If this thread deletes the lost, in the middle of the main thread trying to get lost, an exception will be thrown. So let's run the program. This time is fine. Second time we see this array index out of bound exception. Let's use a debugger to show you what will happen. Okay, let's put a breakpoint here and a breakpoint here, and let's run the program. Debugger. Yes. Okay, at this point we only have the main thread. In the next breakpoint, our thread will be started. Okay, let's run through this step. After start, we have two threads. The main thread is about to get, and the other thread is trying to remove. Okay. If we allow the main thread proceed, at this point, the last index it sees is let's go to the next step. The last index it sees is 9. Okay, so the list at this point have 10 elements. So the last index 9 refer to the 10th element. And here let's allow the other thread remove it. Remove one element. So if we go back to checklist, it only have 9 elements. So, but the main thread is still see the last index as 9. So it's trying to get the 10th element, which is already been removed. You see, the element count is only 9. You're trying to get the 10th. Of course, you will get a array index out of bound exception. You see, the exception is thrown. Okay, and we allow the other thread to run to finish as well. This is not always the case, so let's create another race condition. And we have the main thread. We let it run to the breakpoint, and we allow it to run through. So we have two threads. The other thread is trying to remove, but before it removes the list, let's allow the main thread to proceed to finish. Okay, you see the index as 9, last index as 9, and the array at this point is 10. And before this thread remove, the main thread can run through the get, and it won't see any index out of bound exception. It can run to finish. Okay, now the other thread can run to finish too, and remove the element as designed. We didn't see any exception this time. So depending on which one wins, we saw different results. How to fix this? We don't want to check, then act. We want those two steps run in atomic steps. So in order to do that, we can use synchronized. Synchronized on a lock. Which lock should we use? How about use this? It won't allow because this is a static method. We cannot use this. So then which lock should we use? One choice is we can use the class as a lock. Okay. And this will work because at any time, only one block can hold the class as a lock. We can run the debugger and see what will happen. Okay. Why don't you put a breakpoint on the synchronized? Whatever. Let me run the debugger. Okay, run to the next breakpoint. Run to the next breakpoint. Okay, you see, the thread is held in the lock. You see, and at that time, the main thread cannot proceed because it needs the lock in order to proceed. So the only thread can proceed is the other thread, and let it run to finish. Now this thread exits. Main thread now held the lock and can proceed. And the last index it stores is 8 instead of 9, so it won't have any problem of running through it. Now it is also run to finish. We didn't see any problem. And let's go. But the right lock we should have held is a lock the vector held. What's the lock the vector is using to guard its or its public methods like the size, get, and remove. The vector use the collection itself as a lock. So when we use the client-side lock, we should use the same lock the vector is using. The right lock should be the list. Okay. If we run this program again, let's use the debugger. Let's use the debugger, and now make it smaller. Oh. run to the next breakpoint, run it through. We have two blocks. Now, both is about to, okay, let main thread run to this line. Both is about to run the synchronized block. Let's say the main thread get the lock first, and it owns a vector. So if we go back to the other thread that is trying to hold the lock, okay, it cannot, and it's gray out because the lock is already held by the main thread. Only main thread can proceed at this time, so we let the main thread run to finish. Now the other thread get a chance to hold the lock and be able to run through the synchronized block. Okay, now both threads have succeeded. So by using the client-side lock and use the correct lock, we can fix the race condition, make this block atomic, make this block atomic too. That's a topic of this section. Oh, okay.